In this video, I'm going to be covering section 5-1, probability distribution. So this is the first chapter, or first section rather, in chapter 5. And this is the first introduction into a probability distribution. So I kind of want to give you guys an overview of what's to come in the next few sections. So chapter 5 is on discrete probability distribution, and chapter 6 is on continuous probability distribution. So chapter 5 is discrete, whereas chapter 6 is on continuous probability distribution. Again, there's two types of probability distribution, and chapter 5 is on discrete, chapter 6 on continuous. If you guys remember back to chapter 1, a discrete data set is where the possible data values are countable. Usually that means whole numbers, and whereas continuous, it's not countable because it's like all real numbers where the values can take on decimal numbers and whatnot, and you can't really count them. All right. So let's go ahead and jump right into it. Let me erase this. Okay, so the pre-skill asks, it says a coin is flipped 2 times. Create the sample space of possible outcomes in 2 flips. Let H represent heads and T represent tails. So 2 flips is not too difficult. So if we want, we can create a tree diagram. Right? It's not too hard. Let's go ahead and do that. Or alternatively, we can just think about it and look and list all of the possible outcomes. For example, when you're flipping two coins, one outcome would be getting 2 heads, right? And then another one would be getting a heads the first flip and then a tails. And then the next one would be like a tails and then a heads, and then the last one would be 2 tails. Again, you could use a tree diagram, and likewise you would get like heads, tails, heads, tails, heads. But something that's small or something that's simple, you don't really need it. All right, so let's take a look at 2 definitions. The first one is random variable. So random variable, we usually represent or let the capital letter X be our notation for random variable, is a variable that has a single numerical value determined by chance for each outcome of the procedure. So X is just the variable, like a dummy variable that we use to represent the data which we're looking at, which we're looking at, right? So for example, like X can be like the number of heads in 2 flips. All right. And then the next definition, which is pretty important, a probability distribution gives the probability of values of a random variable. So a probability distribution is often expressed as a table, a formula, or a graph, right? So let's take a look at an example of a probability distribution, a very simple one. So here we have the probability distribution for the number of heads in 2 flips. And it says represent the probability for the number of heads in 2 flips using the table and graph. So I already have the graph here written for us or drawn for us, but let's take a look at the table. So X is the number of heads possible in 2 flips. So when we're flipping a coin 2 times, there are how many possibilities are for the number of heads. So earlier in our pre-skill, we had the following sample space. So for example, like the first one, actually let's start with like this one, just so it's in order of smallest to least. X's. So there can be no heads, right? That's where you get 2 tails. And then there can be 1 head. That is, we have 2 possible ways to get 1 head, but well, let's write down the x's first. So there can be one head, and then there can be two heads, right? A head and a head. All right, and then this column is our probability for each of the x. So for example, here for the probability of no heads would be for us to ask ourselves. It would be the question. How many possible ways can we get no heads over the total number of outcomes, right? That's the probability. That would give us the probability of no heads. So there's one way we can get no heads. That's if we get two tails over 4 possible outcomes, because there's 1, 2, 3, 4 possible outcomes. All right, and we can turn that into a decimal by dividing 1 divided by 4, which is equal to 0.25, right? Now, what's the probability of getting one head? Well, how many different ways can we get one head? 2 different ways, right? That's if we get a head and then a tails, or if we get a flip a tails and then a heads. So that's 2 over 4. So that's going to be, if we change that to a decimal, that's going to be 0.5. And then the last one, the probability that we get 2 heads. So how many different ways can we get 2 heads? Well, that's only one way. That's if we get heads and a heads, right? So that's going to be 1 over 4 possible outcomes. So that's going to be 0.25 as a decimal. Okay, so this is, I'm going to erase this these fractions here. This is a probability distribution in table form, and this is the same probability distribution, but then this is in graph form. So you're going to see it again. You're going to see a probability in 3 different forms: a table, a formula, or a graph. So in this case, we looked at the table form and a graph form. Sometimes there's not a formula form. Sometimes there is. Sometimes we're not going to look at the formula for certain cases. So for this one, we didn't need a formula for that, right? We could have just used a table. There are 3 requirements to be a probability distribution for a numerical variable, and that is, the first one is that the random variable, we have a numerical random variable associated with corresponding probabilities. So we have a numerical random variable, and that's kind of the key word right there. It's got to be a numerical random variable that corresponds with probabilities, right? The second requirement is that the sum of the p of x's, again, if you guys remember, this notation is the sum notation, right? And it says the sum of the p of x's, the sum of the probabilities, is equal to 1. So that's the second requirement. And then the third requirement says that the p of x's, the probabilities, have to be like true probabilities. So in other words, they have to be between 0 and 1 inclusive, meaning they could be 0 or 1, right? So you have to meet those 3 requirements to be able to be a probability distribution. Okay, so let's take a look back at this example just to confirm that it meets those 3 requirements. And I have the same probability distribution right here. So determine whether the following describes a probability distribution: the number of heads in 2 coin flips. All right, so requirement number 1 says that x is numerical. That's primarily the main thing that you can take out of the first requirement. And we know there's a probabilities associated, so we just have to check whether it's numerical, right? Well, that one's pretty simple, right? All of these are numbers, so that one checks off. Requirement number 2 says the p of x's, the sum of the p of x's, is equal to 1. Well, let's see. We have 0.25, which is a quarter, right? And then plus 0.50, which is 50 cents, plus 0.25, which is a quarter. So that makes $1, which is adds up to 1, right? So that checks off. Requirement number 3 says that the p of x's, the probabilities, each of the probabilities, so each of the individual probabilities are between 0 and 1. Well, this one's between 0 and 1. This one's between 0 and 1. And this one's between 0 and 1. So that one checks off, right? So if he checks off all 3 requirements, then we know that it's a probability distribution. So yes, probability distribution. Okay, let's take a look at number 2. So number 2, we have should marijuana use be legal? So our X here is the response. Yes, no, don't know. So let's check our 3 requirements. Is X numerical? Clearly it's not, right? So in this case, the variable is tracking the response of the subjects in the survey. So this is not numerical. So immediately we know that this is not a probability distribution. So we can stop checking those other 2 requirements, but just for the sake of it, just get a little bit of practice. Let's go ahead and just check it. So the second requirement says the sum of the p of x's, right? The sum of the probabilities is equal to 1. So let's go ahead and just check on this one. And let me pull out my calculator just to show you guys, just to add it using that. So 0.42 plus 0.51 plus 0.07. Let's see if that is equal to 1. Yes, it is. So that second one checks off. The third requirement says the individual probabilities has to be between 0 and 1. So in other words, they have to be true probabilities, right? So is 0.42 between 0 and 1? Yes, it is, right? Is 0.51 between 0 and 1? Yes, it is. Is this one between 0 and 1? Yes, it is. So it all checks out. So that one checks out. But we know that this is not a probability distribution because it fails the first requirement. All right. So one of the things that you're going to be doing given a probability distribution in tables is to calculate the parameters given a probability distribution. And we're going to be doing it various ways. The first way is using a table. So this is calculating parameters for probability distribution when you have the table form. So when you have the table form. These are the formulas for the parameters. Again, parameters are population values, right? Numerical values related to the population. So the mean, population mean is the most popular one, right? And the population variance is sigma squared. And then the population standard deviation is sigma. So these are the formulas, but in this class, we're not going to be using these formulas. So instead, we're going to be using the TI calculator. And here are the steps. So the steps are you want to input the x into one list, L1, input the p of x's into another list, say L2, and then we're going to run one var stats on L1 and L2. All right, let's see. And then I have a note here. I'm going to be referring to expected value several times in this presentation and throughout chapter 5. The expected value is equal to the mean of the probability distribution. So anytime you have a probability distribution or any situation involving a probability distribution, the value that you expect, the expected outcome, the most likely outcome, is the mean. All right, so let's take a look at these 2 practice problems. So the instruction says to determine whether the table describes a probability distribution. If it does, find the mean and the standard deviation. So we have 3 problems that we have to answer, right? The first one is it a probability distribution, right? And if it is, let's find the mean and let's find the standard deviation. So let's take a look at number 1. So number 1, the random variable x represents the number of girls among 6 births. So among 6 births, you can have no girls, you can have 1 girl, 2 girls, 3 girls, 4 girls, 5 girls, or 6 girls, right? If all of them were girls. And the no girls would be if all of them were boys, right? And these are the corresponding probabilities for each of those. So let's just check those 3 requirements. So requirement number 1 says, is x numerical? So is x numerical? Pretty simple, right? All of these are numbers, all of the x's are all numbers, so we know that that's checks off. Requirement number 2 says the sum of the p of x's, the sum of the probabilities, is it equal to 1? Well, let's check. Let's add up all the probabilities, see if we get 1. Okay, so we're going to just add them up. and we're slightly off, but I believe it's because some of these are rounded probabilities, so which is okay. So as long as you get pretty close to 1, you should be good. So we're going to check off that the requirement number 2 is met. Again, as long as you get pretty close to 1, the sum is pretty close to 1, you should be good. Requirement number 3 says that the individual probabilities, those individual p of x's, is between 0 and 1. Well, let's check. This one's between 0 and 1. This one is as well. This one as well. They're all between 0 and 1. So that one checks off. Now that we've checked it off, all three requirements are met. We know it's a probability distribution. And if it is, then it says, the instruction says find the mean and the standard deviation. So the mean and the standard deviation. And I didn't provide any round off instructions, but let's round to say 2 decimal places. Okay, so here's how you would do it using the TI 84 calculator. So we're going to put the x's in L1 into one list, and then we're going to put the p of x's into a second list, say L2. It's a good practice just to put it in L1 and L2. You can put it in any list you want, but then it's just easier if you chose like the first list and the second list to be like that. So we're going to go to stat, we're going to go to edit, and we're going to input the values. Okay, so I've got my values inputted. So I've got the x's in L1 and then the p of x's in L2. So the next step is you want to run one-var stats, right? So I'm going to exit out of this screen by pressing second mode to quit. And I'm going to go back to stat. And then to get to one-var stats, we're going to go to calc. So press the right button, go to one-var stats, enter that. So the list, I'm going to put my x's, which is my it's in L1, right? So let's say that it wasn't here. I'd have to press second 1 to call L1. And then in my frequency list, I'm going to call L2, which is the p of x's. That's where I store the p of x's. So we're going to press second 2, and then I'm going to go down to calculate. So the mean here is 3, and sigma is the standard deviation, the population standard deviation. That's 1.22. Again, we're rounding to 2 decimal places, and the second 2 is in the round off spot, and the 4 here does not increase it to a 3, so it just stays the same, right? So the mean is 3, and the standard deviation, the population standard deviation, is 1.22. So we didn't need to round the mean because it was a whole number, right? All right, so some of you guys have the older TI-84 or you have the TI-83, and when you go to one-var stats, you don't get this screen. So let me show you guys what you would do. So your screen should look something like this. So here I have the TI-83. So let me show you guys how to do that. So we're going to go to stat. Oops, turn it on. So we're going to go to stat and then calc and then one-var stats. Right? So you get an output that looks like that. So what you're going to do is you're going to call L1. So we're going to press second 1. And then you're going to press comma. So comma is right above the 7. And then you're going to call L2, so you're going to press second 2. And then if you press enter, you would get this output. All right, so that's the TI-83 or the older 84. Okay, number 2. So be a good idea if you guys pause the video and try it yourself. All right, so here's how you do it. So again, step 1, the instruction says to check whether it's a probability distribution first, right? So let's go ahead and check those 3 requirements. Requirement number 1, are the x's numerical? Yes, they are. So that one checks off. Requirement number 2, if I add the p of x's, do I get 1? Well, let's take a look. Let's go ahead and add it, see what we get, right? So that's going to be 0.365 plus 0.445 plus 0.161 plus 0.029. Okay, so sure enough, you get 1. So that one checks off. Requirement number 3 is you want to check whether each of these individual probabilities are between 0 and 1. Yes, 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 and yes, right? So that one checks off. So usually it's a red flag. The only time where the P of X is not between 0 and 1 is if you get a negative number or a number greater than 1, right? Then that wouldn't be between 0 and 1. Again, if you guys recall, probability ranges from 0 to 1, right? You can only have a probability, a valid probability ranges from 0 to 1. All right, so now if we have that, well, now that we have that it's a probability distribution, we can calculate the mean and the standard deviation. Okay, so similar. So let's go ahead and just jump right in here. So we're going to go to press stat, edit, and I'm going to clear these two lists. So I'm going to press up until the list is highlighted, press clear, press down. Likewise, go up to L1, make sure it's highlighted, press clear, and press down, and then just put in the values that I want. Do same here. Okay, so once we have those two lists, we're going to go to stat, calc, one var stats, list 1, list 2, looks good. And there it is. So if we're rounding to 2 decimal places, this would be 0.85. And then the standard deviation, the population standard deviation would be 0.79, right? Okay, so that's that. Let's take a look at, I'll let you guys try these 3 and 4. And I just want to remind you guys, for a problem like this, please check those 3 requirements. If one of the requirements doesn't pass, then you would just stop there. So for example, one of these, as I recall, one of these is not a probability distribution. So if you check those 3 requirements and one of them doesn't pass, and it's not a probability distribution, you just stop. You don't have to calculate the mean or the standard deviation. All right, so the next concept in 5-1 is significant results. So this is moving into something that's very important moving forward. So in any statistical study, we want to recognize significant results, right? Whether something is significantly low or if something is significantly high. And we've already looked at one method with using the range rule of thumb, right? The range rule of thumb provides us a tool to identify significantly low or significantly high values. We're going to use a more, more widely used method in the statistical world, more robust method, and that is using probability. So using probability to identify significant values is usually tougher for students. This one is not as tough. But let's go ahead and tackle this one, and then when I get to this one, I'm going to slow down a little bit and be a little bit more thorough so you guys understand how to do it, how I'm doing it, right? Okay, so here in this example, we have number of girls. The table below shows the probability distribution for the number of girls in 8 bursts. Find the mean and standard deviation, round to 1 decimal place, and then we're going to use the range rule of thumb to determine whether the following is significantly low, significantly high, or not significant at all, right? So here we have the probability distribution, and I'll just tell you, I've verified it. This is a probability distribution. You do not have to go through those 3 steps. I'll just declare to you guys that it is. So we know that given that this is a probability distribution, to find the mean and the standard deviation, we just have to do that with a calculator, right? So we're going to go to stat, edit, and then input all those values, right? So in the L1, I inputted the X's. These are the possible number of girls in 8 bursts, right? You can have no girls all the way up into all girls. And then these are the associated corresponding probabilities for each of this situation. All right, so then from here, we're going to go to, we're going to run one var stats. So we're going to click stat, calc, one var stats, and do L1 and L2. And then calculates, and it looks like the mean is 4. Oops. So the mean number of girls in 8 bursts is 4. It makes sense, right? If the probability of having a girl or a boy is a half, right, 50%, then you would expect 4 of them to be girls, 4 of them to be boys as well, right? And then the standard deviation would be 1.4. So it says round to 1 decimal place, so we get 1.4. All right, now to answer this, the real question, using the range rule of thumb, would the following be significant? No girls out of 8 births, would that be significant? What about 6 girls out of 8? What about 7 girls out of 8? All right, so using the range rule of thumb, if you guys recall, so I'm going to draw it up here, just the number line, or a line, number line, I guess. So this is for the number of girls, right? Number of girls in 8 births. Okay, so we know that it ranges from 0 to 8. In the middle, which is what we expect to have, the number of girls expected, which is the mean, is 4. And according to the range rule of thumb, significantly low values are 2 standard deviations below the mean or lower, right? That's what this is stating. Mean minus 2 times the standard deviation or lower. So let's go ahead and calculate that using the calculator. So the mean is 4. So we're going to subtract 2 times the standard deviation, which is 1.4. So it looks like if the number of girls is 1.2 girls or smaller or less or lower, then that's significantly low. And then the significantly high would be 4 plus 2 times 1.4. So significantly high would be 6.8 girls or higher. All right, so again, this is sig low. This is sig high. And right in the middle would be not significant. Right? And this makes intuitive sense, right? This makes intuitive sense because, to state it quite simply, when we're having 8 kids, we would expect half of them to be girls. And the farther we get away from 4, let's say the more girls we get, it would start to be significant, right? So if somebody had 8 girls out of 8 births, somebody had 8 kids and they had 8 girls, you would be surprised, right? That would be kind of surprising. So we would say it's significantly high. And according to the range rule of thumb for this situation, 6.8 girls or above is significantly high. Likewise, if they have like few girls, right? So again, we expect about around 4, half of them to be girls. If they had 3 girls, you wouldn't be that surprised, right? Because 3 is not that far from 4. If they had 2 girls, you wouldn't be too surprised. But then if they had 1 girl, then you would start to say, hey, that's 1 girl out of 8 births. That's kind of low, right? So the range rule of thumb says 1.2 or below would be significantly low. And now to answer the questions down here, so is no girls significant? It is, right? So no girls falls in the significantly low. So no girls is sig low. What about 6 girls? 6 girls, 6 is higher than 4, but is significantly high. No, it's not. Not according to the range rule of thumb, right? Because it has to be 6.8 girls or more. So this is not sig, not significant. What about 7 girls? Well, 7 girls, it falls right in the significantly high. So yes, it is. It's sig high. All right, so that is calculating or determining whether a result is significant using the range rule of thumb. So let's go ahead and take a look at probabilities. And again, probabilities is a little bit tougher, so I'm going to spend a little bit more time on that. Okay, so for probabilities, for using probabilities to determine whether something's significantly high or low, we have the following. It says significantly low, a result is significantly low if the probability of that value or lower is less than or equal to 0.05. And a result is significantly high if the probability of the result or higher is less than or equal to 0.05. Now, this is not a typo. The less than or equal for both sig low and sig high, that was not a typo. Take note, When we're calculating when something is significantly low, we are calculating the probability of that value or lower. And when we calculate, if we're determining whether something is significantly high, we calculate the probability of that value or higher. Now, let me try to make sense of this. So, think about this for a moment. And I'm gonna look at this. I'm gonna be referring to this while I'm doing this example. So, probability ranges. Probability. First of all, probability measures the likelihood or the chance of something happening, right? Where zero, probability of zero indicates that that event is impossible. Oops. Okay, and then a probability of 1 implies that the event is for sure going to happen. 50-50, 0.5 says there's a 50-50 chance. And then any probability, the probability of an event that's close to 0 is very unlikely. So this is any probability close to 0 indicates an event that is very unlikely. So for now, we're going to use a probability like 0.05 to indicate that a probability that of an event that is very unlikely to occur. So very unlikely. So 0.05 and below. Okay, so think about that. All right. So imagine this scenario here. So I'm going to delete this for a sec. Oops. So I'm going to delete this for a sec, and you guys kind of think about this. So we know that in 8 bursts, we expect around 4 of them, assuming that boys and girls are equally likely. What are the chances? Tell me the probability of exactly 4 bursts. So think about that. So that should be around, your chances of having 4 bursts should be, you should be thinking something like 50-50 chance, right? 50-50 chance here. Well, what happens if I move away from the 4? Let's say to the right side. Like, what are the chances of that I have, say, 5 kids? Would that probability, would it go up or would it go down? What about 6? With that probability, what's the probability of having 6 out of 8 girls? Would that probability go up or go down? And what about 7 girls out of 8 births? Would that probability go up or go down? So you should be thinking the chances of having 7 or 8 girls, the further I move away from 4, right? Especially if I move, let's say, 8 girls, that probability should be low. If somebody said, I want to have 8 kids, what's the chances that all 8 are girls? You would say that chance is not that good, right? In other words, you're saying the probability is low that that's going to happen. So just remember, the further away we move from what we expect, again, 4 is the expected value, right? The lower the probability. All right, so all girls, low probability. Oops, actually I needed that. So all girls equals low probability. Now, what about what are the chances as I move to the left? Let's say let's say 4 girls out of 8 births is 50-50, 0.5 probability. What happens? What's the probability of 3 girls? Is that going to go up or is it going to go down? Right? So if somebody says 3 out of 8 births, 3 girls out of 8 births, what about 2 girls? What about 1 girl? What about no girls, right? So what happens as I move closer to the left, or as I move away from 4 going to the left? So 2 girls, what's the probability of 2 girls out of 8 births? Would that probability be less than 0.5? Probably, right? Because you're thinking the chances are Well, we expect 4, and the further we move away from to the left, that's very unlikely to happen. So like if we go to the extreme and say no girls out of 8 kids, that's also a low probability. So that's where we get this less than or equal to 0.05. It's because the further away when we're dealing with probability and using probability to determine whether something is significantly low or high, we want to look at low probabilities. The event has to be a low probabilities in order to be significant. And the further we move away from what we expect, which is the mean, the lower the probability. And when we move so far away to the extreme, let's say that 8 girls out of 8 births, that probability should be low, which would indicate that it's significantly high, right? So if the probability, like the probability of 8 girls is low, which is it should be, it would be significantly high. Likewise, if we go all the way to 0 girls, which is also very unlikely to occur, we would say that is significantly low because the probability, we should expect the probability to be low because that's very unlikely to occur, right? So significantly low. So now all of that explanation to answer the following question. So here we have use probability to determine whether the following is significantly low, significantly high, or not significant at all. So what about no girls? So using probability, we would look at the probability of 0 or less or lower, but then you can't get any lower than 0, right? Number of girls is 0, right? You can't get negative girls, in other words. So what is the probability of 0 or lower? Well, that's just the probability of 0. So that's going to be 0.00391. And sure enough, is it lower than 0.05? Right, that's where it's very unlikely. That area right there it's where it's unlikely, and yes, it is, right? So it's less than or equal to 0.05, which indicates that it's significant. It's significant, and we're going to say that it's significantly low. Why are we saying it's significantly low? Well, it's because it's less than what we expect, right? Because 4 is what we expect. 0 is less than 4. Is it significantly low? Yes, it is, because the probability of it is very small. So now let's take a look at 6 births. So 6 births. We're going to ask the question, is it significantly high? Why are we asking that question? Why are we going to check whether it's significantly high? It's because 6 is greater than the expected value, which is 4, right? So because we're checking whether it's significantly high, we're going to calculate the probability of 6 or higher. So 6 or higher. Which is equal to, well, let's see, 6 or higher is 6 or 7 or 8. So in other words, we're just going to add these 3 probabilities, right? So let's go ahead and do that. So we're going to do that. So we're going to take 0.10937 plus 0.03125 plus 0.00391. And that's what we get, 0.14453. So 0.14453. Now, it would be significantly high if the probability is less than or equal to 0.05, which it clearly is not. It's greater than 0.05, which means it's not significant. So the probability of getting 6 girls is not low enough to where we're going to say that was probably very unlikely to happen. So we're going to say it's not significant. Only events where it's very unlikely to occur are we going to say that it's significant. And whether it's significantly low or significantly high depends on where it falls, right? If it's less than the expected value, then we say significantly low if its probability is low. And if it's higher than the expected value, then we say significantly high if its probability is small. Okay, so let's look at the last one, C, which is 7 girls. So 7 is higher than 4, which is the expected value. So we're going to check whether 7 is significantly high. So we're going to calculate the probability of 7 or higher. So that we're going to calculate the probability of 7 or higher. So 7 or higher, what does that mean? So 7 or higher means 7 or 8. Okay, so the probability of 7 is this, and the probability of 8 is that. Let's go ahead and add the two probabilities. So 0.03125 plus 0.00291, 391, and we get that. So 0.03516. So 0.03516. Just double check. Yep. Okay, so clearly this is less than or equal to 0.05, right? Which means that it's significant. So when when an event has a low probability, we say significant. Now, is it significantly high or low? It's significantly high. Why is that? It's because the value we were looking at, 7 girl births, is higher than what we expect, right? So 7, we were asking, is 7 significantly high? Yes, it is, right? Is it significant? It is. It's high, and it's significantly high because its probability is less than or equal to 0.05. All right, so I'm going to stop there. That concludes section 5.1. In the next video, we're going to talk about something that's very important in this chapter, and that is the binomial distribution.